students, in this lecture we will see why we require Miller theorem and how to apply that Miller theorem when a component is present between input and output. So Miller theorem basically किधर यूज होता है? When there is an element present between output and the input terminal. So if you see here, this CBC, this stray capacitance, or you can say parasitic capacitance, is present at high frequency. Then this CBC has to be splitted into two parts, one at the input side and other part of the CBC at the output side. So how to split this CBC into two parts, that we have to decide, and for that purpose we require Miller theorem. Now consider that there is an element Z over here and the amplifier gain is K. So if the voltage is V1 at the input side, the output voltage is V2. So V2 is nothing but K times V1. Now if you are talking about current I1 over here, there is an already designed amplifier over there, and just I am splitting this Z element over here. So I1 can be written as V1 minus V2 by Z. Now what part of Z will get reflected at the input side? So here we have to form the equation in terms of V1 and I1. Rather we have to find out the ratio of V1 by I1. So substitute for V2. So this turns out to be V1 minus K times V1 by Z. So you can take V1 common and V1 by I1 turns out to be Z divided by 1 minus K. So how to split the given element at the input side? Divide that by 1 minus K. Let's say this Z is nothing but a capacitor. So the input part of this capacitor is nothing but V1 by I1, which is equal to 1 by j omega c divided by 1 minus K. That is nothing but 1 divided by j 1 minus K omega c. Now V1 by I1 is impedance. So here the impedance, net impedance, is nothing but 1 minus K times omega c, or the capacitor that is present at the input side will be 1 minus K into c. Similarly, अभी output side पे क्या part आएगा वो आपको देखने का है. So we have to write down the equation for I2. I2 किधर है? ये इधर है I2. I2 का फॉर्मूला क्या रहेगा? V2 minus V1 by Z. Now find out ratio of V2 by I2. For that purpose, substitute for V1. So I2 is nothing but V2 minus V1 हो जाएगा V2 by K divided by Z. So V2 you can take outside and this will become K minus 1 divided by KZ. So the ratio V2 by I2 is nothing but K times Z divided by K minus 1. Now if this impedance is capacitive reactance, then this ratio will be K divided by K minus 1 and Z is nothing but 1 by j omega c. So this is equal to 1 divided by K minus 1 into j omega c by K. So the capacitance that is present at the output side can be represented as K minus 1 by K into C. So this is equal to 1 minus 1 by K into C. Similarly, here the input capacitance Ci can be represented as 1 minus K by C. K क्या है? K is nothing but voltage gain. So how to split the element into two parts that we have seen. अगर ये खाली रेजिस्टर रहता था तो कुछ प्रॉब्लम नहीं. रेजिस्टर को खाली आपको डिवाइड करने का रहता है 1 माइनस के से, या फिर इसको मल्टीप्लाई करने का रहता है k डिवाइड बाय k माइनस 1 से. सो अभी इसका यूज क्या हुआ? तो अभी हम लोग हाई फ्रीक्वेंसी रिस्पॉन्स देखेंगे एंड विल सी दैट दिस कैपेसिटर CBC इज प्रेजेंट बिटवीन इनपुट एंड आउटपुट. सो इसको आपको दो पार्ट में स्प्लिट करने का है. सो CMI, Miller capacitance at the input side. M stands for Miller and I stands for input side. That will be calculated as 1 minus K times C. So उसका वैल्यू हो जाएगा 1 minus AV. AV is nothing but voltage gain. इधर मैंने K ये voltage gain लेके ये फॉर्मूला डिराइव किया था into CBC, while the Miller capacitance at the output side will be represented as 1 minus 1 by AV into CBC. So तभी ये डेरिवेशन में नहीं करूँगा, ये डायरेक्टली फॉर्मूला में यूज कर दूंगा. सो काफ़ी सिंपल है मिरर थ्योरम. ये कैसे स्प्लिटिंग होता है ये देखने के लिए आपको ये छोटा सा डेरिवेशन याद रखना पड़ेगा. कुछ नहीं है, ये खाली V2 इज इक्वल टू KV1 फाइंड आउट करो. फर्स्ट यू फाइंड आउट द रेशियो ऑफ V1 बाय I1 and second time you find out the ratio of V2 by I2. And since Z we are considering as capacitor, remember Z has to be replaced as 1 by j omega c. So that's it for the Miller's theorem. In the next lecture we will see the high frequency response of BJT amplifier. Thank you.